Google Cloud Platform, Identity and Access Management for AWS Power Users. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we will explore Google Cloud Platform Identity and Access Management from the perspective of someone who already knows AWS IAM inside and out. If you have been working with AWS policies, roles, and permissions, you will find that GCP takes a fundamentally different approach to solving the same problems. Understanding these differences is crucial for successfully working in a multi-cloud environment or migrating workloads from AWS to GCP. The core philosophy differs between these two platforms. AWS IAM is policy-centric, where you attach JSON policy documents to identities or resources. GCP IAM, on the other hand, is binding-centric, where you bind members to roles at various resource hierarchy levels. This fundamental difference affects how you think about and implement access control. Throughout this presentation, we will map familiar AWS concepts to their GCP equivalents. We will cover identity types, policy structures, role definitions, trust relationships, and resource-level permissions. By the end, you will have a clear mental model for translating your AWS IAM knowledge into effective GCP IAM configurations. Fundamental architecture differences. Let us begin by examining the fundamental architectural differences between AWS IAM and GCP IAM. In AWS, you have a flat account structure where IAM policies are the central mechanism for defining permissions. Policies are JSON documents that specify which actions are allowed or denied on which resources, and these policies are attached to users, groups, or roles within the account. GCP takes a hierarchical approach with its resource hierarchy. At the top sits the organization, followed by folders, then projects, and finally individual resources like compute engine instances or cloud storage buckets. This hierarchy is not just organizational, it directly affects how permissions are inherited. When you grant a role at the organization level, that permission automatically flows down through all folders, projects, and resources beneath it. The diagram on the slide illustrates this key difference. In the AWS model, you see users and roles within an account, with policies attached to these identities. There is no inherent hierarchy beyond what you create with AWS organizations. In the GCP model, the organization sits at the top, with folders providing logical grouping, projects containing actual resources, and permissions cascading downward through this structure. This hierarchical inheritance model in GCP means you need to carefully consider where you grant permissions. A role granted too high in the hierarchy will propagate everywhere below it. AWS administrators often apply the principle of least privilege at the individual resource level, while GCP administrators must think in terms of hierarchy levels and strategic placement of role bindings. Identity types comparison. Now let us compare the identity types between AWS and GCP. In AWS, you work with IAM users, which are permanent identities with long-term credentials. These users can have passwords for console access and access keys for programmatic access. AWS also has IAM groups, which are collections of users that share the same permissions, and IAM roles, which are assumable identities for temporary credential scenarios. Google Cloud Platform does not have the concept of IAM users in the same way. Instead, Google Cloud Platform uses Google accounts, which are the individual email addresses from Gmail or Google Workspace. These are managed outside of Google Cloud Platform IAM. They exist in Google's identity system and are simply referenced in Google Cloud Platform IAM Bindings. This is fundamentally different because you do not create or manage user credentials within Google Cloud Platform itself. For groups, AWS has IAM groups that exist within the AWS account. GCP uses Google Groups, which are managed in Google Workspace or Cloud Identity. These groups contain Google accounts as members, and you reference the entire group in IAM Bindings by its email address. Service accounts deserve special attention because they exist in both platforms, but work differently. AWS IAM roles are used for service-to-service authentication. An EC2 instance assumes a role to get temporary credentials. GCP service accounts are actual identities, like special user accounts for applications. They have their own email addresses and can have keys generated for them. You attach service accounts to GCP resources like compute engine instances, and that resource then operates with the permissions granted to that service account. The table on the slide provides a direct mapping. AWS IAM user maps to Google account, IAM group maps to Google group, and IAM role maps to service account plus IAM role combined, because GCP separates the identity aspect from the permission granting aspect. AWS IAM policy structure. Before we dive into GCP policies, let us review the AWS IAM policy structure that you are already familiar with. AWS IAM policies are JSON documents with a specific schema. The version field specifies the policy language version, and you should always use the current version, which is the 17th of October 2012. The statement field contains an array of individual permission statements. Each statement has several key elements. The effect field specifies whether the statement allows or denies access, with possible values of allow or deny. The action field lists the specific API operations being permitted or denied. These follow the format of service::action, such as S3::getObject or EC2::describe instances. You can use wildcards with the asterisk character for broader permissions. The resource field specifies which AWS resources the actions apply to, using Amazon Resource Names, or ARNs. An ARN uniquely identifies a resource and includes information about the service, region, account, and specific resource ID. You can also use wildcards here to match multiple resources. The condition field is optional, but powerful. It allows you to specify circumstances under which the policy takes effect. You can create conditions based on IP addresses, time of day, whether MFA was used, tags on resources, and many other factors. This granular control is a strength of AWS IAM policies. Looking at the code example on the slide, you see a policy that allows reading from a specific S3 bucket. The effect is allow, the action is S3::getObject, and the resource is the ARN of the myBucket bucket with a wildcard for all objects within it. There is also a condition requiring that requests come from a specific IP range, demonstrating the conditional access capability. Google Cloud Platform IAM policy structure. Now let us examine the GCP IAM policy structure, which is quite different from AWS in GCP. An IAM policy is also a JSON document, but its structure revolves around bindings rather than statements. A binding connects one or more members to a single role. The bindings array contains these binding objects, and each binding specifies who gets what role. The role field specifies the predefined or custom role being granted. Roles in GCP follow the format roles/role name, such as roles/storage.object viewer for read access to cloud storage objects. The members field is an array of identities receiving this role. Members are specified with a type prefix followed by a colon and the ID. Member types include user : for individual Google accounts, service account : for service accounts, group : for Google groups, and domain : for entire Google Workspace domains. There is also all users for public access and all authenticated users for any authenticated Google account. The condition field in GCP bindings allows conditional role grants, similar to AWS conditions, but with a different syntax using Common Expression Language, or CEL. Looking at the code example, you see a GCP IAM policy with two bindings. The first binding grants the storage.object viewer role to a user and a group. The second binding grants storage.object creator to a service account, but only when the resource name starts with a specific prefix. This condition uses CEL syntax where resource.name. Starts with as the condition expression. Notice the key structural difference. In AWS, you define actions and resources in each statement. In GCP, the role encapsulates the actions, and the policy is attached to a specific resource or hierarchy level, which determines what resources the permissions apply to. You do not specify resources within the policy itself because the policy attachment point defines the scope. Roles concept comparison. Let us compare how roles work in AWS versus GCP, because this is where significant conceptual differences emerge. In AWS, when you hear the term role, you typically think of IAM roles, which are assumable identities. An IAM role is an entity that defines a set of permissions, but more importantly, it is something that principals can assume to temporarily become that role. The role has a trust policy defining who can assume it and a permissions policy defining what the role can do. In GCP, the term role refers specifically to a collection of permissions. A GCP role is not an identity you assume. It is simply a named bundle of permissions that you grant to identities through bindings. The identity in GCP is separate from the role. You have Google accounts, service accounts, and groups as identities, and you grant them roles to give them permissions. Google Cloud Platform has 3 types of roles. Basic roles are the original broad roles with names like owner, editor, and viewer. These grant thousands of permissions and are generally too permissive for production use. Predefined roles are created and maintained by Google for specific services, offering granular permissions packages like compute.instance admin for managing compute engine instances. Custom roles allow you to define your own permission sets when predefined roles do not match your requirements. The diagram illustrates this difference. In AWS, you see the IAM role as an assumable entity with its own trust relationship and permissions. In GCP, the role is just a permission bundle that gets bound to members. The GCP service account is the closest equivalent to an AWS IAM role because it is an identity that applications use, but the permissions come from role bindings rather than being part of the service account definition. This separation of identity and permissions in GCP means you manage them in different places. You create service accounts in the IAM and admin section, but you grant roles through IAM policy bindings on resources, projects, folders, or the organization. AWS trust policies and GCP equivalents. Trust policies in AWS define who can assume an IAM role, and understanding their GCP equivalent is essential for architects working across both platforms. In AWS, when you create an IAM role, you must specify a trust policy. This policy uses the same JSON structure as permissions policies but focuses on the principal element, which defines which entities can call the Assume Role API to take on that role's identity. Common trust policy scenarios include allowing an AWS service like EC2 or Lambda to assume a role, allowing IAM users from the same or different AWS accounts to assume a role, allowing federated users from an identity provider to assume a role, and allowing Web Identity Federation from providers like Google or Facebook. GCP does not have trust policies in the same way because GCP roles are not assumable identities. However, GCP has equivalent mechanisms for the same use cases. For service-to-resource trust, you attach a service account to a GCP resource like a compute engine virtual machine or cloud function. That resource then operates with the service account's identity without any assuming process. For cross-project access, you simply add a principal from another project to the IAM binding. There is no trust relationship to establish because identity is separate from the project. For service account impersonation, which is the closest equivalent to assuming a role, GCP uses the service account token creator role. If you grant this role to a user or service account on another service account, they can generate tokens to act as that service account. This is similar to assuming a role in AWS, but requires explicit permission through IAM bindings. The diagram shows AWS trust flow where a principal assumes a role to get temporary credentials, versus the GCP model where principals are directly granted roles or impersonate service accounts. In GCP, the identity remains constant. You either have direct permissions or you impersonate another identity that has permissions. AWS resource policies versus GCP IAM bindings. Resource policies in AWS are a powerful feature that allow you to attach permissions directly to resources rather than to identities. S3 bucket policies are the most common example, but you also see resource policies on SQS queues, SNS topics, Lambda functions, KMS keys, and secrets manager secrets. These policies define who can access the resource and what actions they can perform. In GCP, every IAM policy is essentially a resource policy. When you set an IAM policy on a cloud storage bucket, a pub subtopic, a BigQuery dataset, or any other resource, you are defining who can access that specific resource. The difference is that GCP does not have a separate concept of identity policies versus resource policies. All IAM policies are attached to some level of the resource hierarchy, whether that is the organization, a folder, a project, or an individual resource. This unification in GCP simplifies the mental model in some ways. In AWS, you must consider both the identity policies attached to the principal and the resource policies attached to the target, then understand how they interact. The effective permissions are the intersection or union depending on whether cross-account access is involved. In GCP, you look at the IAM policies on the resource hierarchy from the organization down to the specific resource, and permissions are additive as they inherit downward. The code examples on the slide show equivalent configurations. The AWS S3 bucket policy grants S3 get object to a specific IAM role for objects in the bucket. The G Cloud Platform equivalent is an IAM policy on the cloud storage bucket that binds the storage object viewer role to a service account. The G Cloud Platform approach is more concise because the role encapsulates the permissions, and the binding location determines the resource scope. One important difference is that AWS resource policies can include explicit deny statements, which is important for creating guardrails. GCP IAM policies only allow. There is no way to explicitly deny access through IAM. For deny functionality in GCP, you use organization policies or IAM deny policies, which are separate constructs from regular IAM policies. Permission inheritance models. Understanding how permissions inherit is critical for both platforms, but the models differ significantly. In AWS, permissions generally do not inherit. If you grant permissions to an IAM user, those permissions apply to that user regardless of any organizational structure. AWS Organization Service Control Policies, or SCPs, do create a form of hierarchy, but they only restrict, they do not grant permissions. SCPs define the maximum permissions that accounts in the organization can have, but actual permissions still come from IAM policies attached to identities within each account. Google Cloud Platform's inheritance model is fundamentally different. When you grant a role at any level of the resource hierarchy, that permission automatically inherits to all levels below. If you grant someone the editor role at the organization level, they become an editor on every folder, project, and resource in the entire organization. If you grant a role at the folder level, it applies to all projects and resources in that folder. Project-level grants apply to all resources in the project. This inheritance is additive and cannot be revoked at lower levels through standard IAM policies. If someone has a role granted at the organization level, you cannot remove that specific role from them at the project level. You can only add more roles. For restrictive controls, GCP uses IAM deny policies and organization policy service constraints, which operate separately from the IAM allow policies. The diagram illustrates this difference visually. In AWS, the account is relatively flat, with SCPs providing guardrails but not granting access. In GCP, the organization, folder, project, and resource levels each represent points where you can grant permissions that flow downward. This makes GCP permission planning more strategic because a single binding high in the hierarchy has wide-reaching effects. Best practices in Google Cloud Platform involve granting permissions at the lowest level that makes sense for the use case. Grant broad roles like owner only at specific project levels where needed, not at organization or folder levels. Use groups to manage access so you can add or remove users from groups rather than modifying IAM bindings directly. Mapping AWS to GCP concepts. Let us consolidate what we have covered into a comprehensive mapping table that you can use as a quick reference when working with G-Cloud IAM. This table shows AWS concepts in the left column and their G-Cloud equivalents in the right column, helping you quickly translate your existing knowledge. For identity management, AWS IAM users map to Google accounts, which are managed in Cloud Identity or Google Workspace rather than in GCP directly. AWS IAM groups map to Google Groups, again managed externally. AWS IAM roles, which are assumable identities, map to GCP service accounts combined with IAM role bindings. Remember that in GCP, the identity and permissions are separate concepts. For policy types, AWS identity policies, which you attach to users and roles, correspond to IAM bindings on projects or above. AWS resource policies, like S3 bucket policies, correspond to IAM bindings on specific resources. AWS service control policies map to GCP organization policies, though they work somewhat differently. AWS permission boundaries, which limit maximum permissions, have a partial equivalent in GCP deny policies. For permission mechanisms, AWS managed policies are like GCP predefined roles since both are maintained by the cloud provider. AWS customer managed policies correspond to GCP custom roles. AWS inline policies, which are embedded in identities, do not have a direct equivalent because GCP does not embed policies in identities. For cross-account and federation, AWS cross-account role assumption maps to granting roles to external principals and service account impersonation. AWS SAML federation uses AWS identity providers, while GCP uses Workforce Identity Federation. AWS Web Identity Federation with OpenID Connect maps to GCP Workload Identity Federation. The table also shows command line interface command equivalents. Where you would use AWS IAM commands in AWS, you use G-Cloud projects and G-Cloud IAM commands in GCP. For example, AWS IAM create role becomes G-Cloud IAM service accounts create, and AWS IAM attach role policy becomes G-Cloud projects add IAM policy binding. Keep this mapping handy as you work through G-Cloud IAM configurations. The conceptual translations will help you apply your AWS expertise effectively in G-Cloud environments. Service accounts deep dive. Service accounts are one of the most important concepts to understand when transitioning from AWS to GCP, because they function quite differently from AWS IAM roles. In AWS, you create an IAM role and attach it to a resource like an EC2 instance. The instance then assumes that role and receives temporary credentials through the instance metadata service. The role itself is just a permission container with a trust relationship. In GCP, a service account is an actual identity, similar to a user account but designed for applications and services. Each service account has its own email address in the format name at project.iam.gserviceaccount.com. You can create service accounts, grant them roles just like you would grant roles to human users, and then attach them to GCP resources like Compute Engine instances, Cloud Functions, or Cloud Run services. When you attach a service account to a Compute Engine instance, that instance can access the metadata server to obtain access tokens for that service account. This is similar to how EC2 instances get credentials for their attached IAM role. However, the key difference is that the service account exists as a separate identity that you manage independently. You can see all service accounts in your project, grant them permissions through IAM bindings, and even allow other identities to impersonate them. The diagram shows the lifecycle of service account usage. You create the service account in your project, grant it the necessary roles through IAM bindings, attach it to a resource, and then the resource uses the metadata server to obtain tokens. Those tokens allow the resource to call GCP APIs with the service account's permissions. Google Cloud Platform also provides default service accounts that are created automatically when you enable certain APIs. The Compute Engine Default Service Account and App Engine Default Service Account are common, for example. These default accounts often have broad permissions like the editor role, which is a security concern. Best practice is to create custom service accounts with only the permissions your applications actually need. Service account keys versus AWS access keys. Both AWS and GCP support long-term credentials for programmatic access, but the usage patterns and security implications differ significantly. In AWS, you create access keys for IAM users, which consist of an access key ID and secret access key. These credentials are used with the AWS SDK and CLI for authentication. In Google Cloud Platform, service accounts can have keys generated for them, which are JSON files containing private key material. When you create a service account key, Google Cloud Platform generates a public-private key pair, stores the public key, and gives you the private key in a JSON file. Your application uses this JSON file to authenticate to Google Cloud Platform APIs. However, Google strongly discourages the use of service account keys. The recommended approach is to use attached service accounts for workloads running on GCP, Workload Identity Federation for workloads running outside GCP, and impersonation for development scenarios. Service account keys are security risks because they are long-lived credentials that can be leaked or stolen. The code examples on the slide show the commands for creating these credentials. In AWS, you use AWS IAM create access key with the username parameter to specify which IAM user gets the access key. The output includes access key ID and secret access key that you must save securely. In Google Cloud Platform, you use G-Cloud IAM service accounts keys create with the output file path, IAM account parameter specifying the service account email, and optionally key file type to specify JSON or P12 format. The command creates a JSON file containing the private key, service account email, and other metadata needed for authentication. If you must use service account keys, implement key rotation and monitor key usage through audit logs. GCP provides recommendations to transition away from keys to more secure authentication methods, and you can use organization policies to prevent key creation entirely. Service account impersonation. Service account impersonation in GCP is the closest equivalent to AWS assume role functionality. It allows one identity to act as another service account, obtaining tokens that represent that service account's identity. This is useful for several scenarios including local development, cross-project access, and privilege elevation workflows. To enable impersonation, you grant the service account token creator role to the identity that needs to impersonate. This role is roles/IAM.service account token creator. When a user or service account has this role on another service account, they can generate access tokens, ID tokens, and sign JWTs for that target service account. The impersonation flow works as follows. First, the calling identity authenticates as themselves. Then, they call the IAM Credentials API to generate a token for the target service account. GCP checks if the caller has the token creator role on that service account. If authorized, GCP returns a token that represents the target service account. The caller then uses that token for subsequent API calls. This differs from AWS assume role in an important way. In AWS, when you assume a role, you become that role for the duration of the session, and all subsequent calls use the assumed role's credentials automatically. In GCP, you explicitly request tokens for the target service account and use them for specific calls. Your original identity remains available. The code example shows how to set up and use impersonation. First, you grant the token creator role using G-Cloud IAM service accounts at IAM policy binding. The resource is the target service account, the member is the identity that will impersonate, and the role is service account token creator. Then you can use G-Cloud commands with the impersonate service account flag to run commands as that service account, or use the IAM Credentials API directly to generate tokens for programmatic use. Creating custom roles. Custom roles in G-Cloud allow you to create your own permission bundles when predefined roles do not match your requirements. This is similar to creating customer-managed policies in AWS, where you define exactly which API actions are allowed. Custom roles help you follow the principle of least privilege by granting only the specific permissions needed for a task. In AWS, you create a customer-managed policy by writing a JSON document that specifies actions, resources, and conditions, then attach that policy to users, groups, or roles. In GCP, you create a custom role by specifying a list of permissions, then bind that role to members just like you would bind a predefined role. GCP permissions follow the format service.resource.verb, such as compute.instances.start or storage.objects.get. You can find the complete list of permissions in the GCP documentation, and you can use the G-Cloud IAM list testable permissions command to see which permissions are available for a specific resource. The code example shows the G-Cloud command for creating a custom role. The G-Cloud IAM Roles create command takes the role ID as the first argument, which is the name you want to give your custom role. The project parameter specifies which project will own the role. You can also create roles at the organization level. The title parameter provides a human-readable name that appears in the console. The description explains what the role is for. The permissions parameter takes a comma-separated list of permissions to include in the role. You can also create custom roles from a YAML file, which is useful for complex roles with many permissions. The stage parameter lets you mark roles as alpha, beta, or GA to indicate their maturity. Custom roles at the project level can only be used within that project. For roles needed across multiple projects, create them at the organization level. One important consideration is that custom roles do not automatically update when GCP adds new permissions to services. If a service adds new features, you must manually add those permissions to your custom roles. Predefined roles maintained by Google automatically include new permissions. AWS Managed Policies versus GCP Predefined Roles. Both AWS and GCP provide pre-built permission sets maintained by the cloud provider. In AWS, these are called AWS Managed Policies. In GCP, they are called predefined roles. Understanding the differences helps you choose the right approach for your access control needs. AWS Managed Policies are JSON policy documents that AWS creates and maintains. They cover common use cases like administrator access, power user access, read-only access, and service-specific policies like Amazon S3 read-only access. You attach these policies to IAM users, groups, or roles. AWS updates these policies when services add new features or when security best practices change. GCP predefined roles work similarly, but are tightly integrated with the GCP resource hierarchy. Each GCP service has a set of predefined roles that grant appropriate permissions for common tasks. For example, Compute Engine has roles like compute.admin, compute.instanceadmin, compute.viewer, and compute.network-admin. Storage has roles like storage.admin, storage.object-admin, storage.object-viewer, and compute.object-creator. The naming convention for GCP predefined roles follows the pattern roles/service.role name. The role name often indicates the level of access, with admin providing full control, viewer providing read-only access, and specific roles like object creator providing limited write access. The table on the slide maps common AWS managed policies to their GCP predefined role equivalents. Administrator access maps to roles/owner, which grants full control over all resources. Power user access maps to roles/editor, which allows modification but not IAM changes. View-only access maps to roles/viewer for read-only access. Service-specific policies map to service-specific roles with similar permission scopes. One advantage of GCP predefined roles is their granularity. While AWS managed policies often grant broad access to an entire service, GCP predefined roles are more fine-grained. For instance, you can grant compute.network-admin to allow network configuration without granting compute.instance-admin for instance management. This granularity helps implement least privilege more effectively. IAM conditions in GCP. Conditional role bindings in GCP allow you to grant permissions that only take effect when certain conditions are met. This is similar to the condition element in AWS IAM policies, but GCP uses a different syntax called Common Expression Language, or CEL. Conditions add another layer of access control beyond just who has a role. AWS conditions use a JSON structure with condition operators like string equals, IP address, date greater than, and bool. You specify the condition key and value within the condition block of a policy statement. AWS provides many context keys for different attributes like source IP, time, MFA status, and resource tags. Google Cloud Platform conditions use CEL expressions, which are more readable and powerful than the AWS JSON syntax. CEL supports logical operators, string functions, and type checking. You write conditions as expressions that evaluate to true or false. If the expression is true, the binding applies. If false, the binding does not grant access. Common condition attributes in GCP include request.time for time-based access, resource.name for resource name patterns, resource.service for service-specific conditions, and resource.type for resource type filtering. You can also use attributes like destination.ip and destination.port for network-related conditions. The code examples show equivalent conditions in AWS and GCP. The AWS example uses a date greater than and date less than condition to restrict access to a specific time window. The GCP example achieves the same result with a CEL expression that checks if request.time is within the specified range. Notice how the GCP syntax is more compact and readable. Another example shows resource name-based conditions. The GCP expression uses resource.name. Starts with to restrict access to objects with a specific prefix. This is similar to the AWS string-like condition on the S3 prefix key, but uses a function call syntax instead of pattern matching. Google Cloud Platform conditions have some limitations. Not all roles support conditions, and the available attributes vary by resource type. You can check the IAM documentation to see which roles and resources support conditional bindings. Workload Identity Federation. Workload Identity Federation in GCP is the equivalent of AWS Web Identity Federation and SAML Federation combined. It allows workloads running outside of GCP to authenticate to GCP services without using service account keys. This is crucial for multi-cloud environments and CI/CD pipelines running in external systems. In AWS, you create an identity provider in IAM, either SAML or OIDC based, and then create IAM roles that trust that identity provider. External identities can then assume those roles to get temporary AWS credentials. Common use cases include GitHub Actions accessing AWS resources or applications running in other clouds. Google Cloud Platform Workload Identity Federation uses a similar model but with different terminology. You create a workload identity pool, which is a container for external identities. Within the pool, you create providers that represent the external identity systems, for example, AWS, Azure AD, GitHub, or any OIDC-compliant provider. You then grant IAM roles to identities from these providers. The federation flow works as follows. The external workload obtains a token from its identity provider, such as an AWS STS token or GitHub OIDC token. It sends this token to GCP Security Token Service requesting a GCP token. GCP validates the token against the configured provider, maps the external identity to a principal in the workload identity pool, and returns a GCP access token. The workload uses this token to access GCP resources with the permissions granted to that principal. The diagram on the slide illustrates this flow for both AWS and GCP. In AWS, the external identity gets a token from GitHub OAuth IDC, calls assume role with web identity, and receives temporary credentials. In GCP, the external identity gets a token from GitHub OAuth IDC, exchanges it at the Security Token Service, and receives a federated access token that can be used directly or exchanged for a service account token. Workload Identity Federation eliminates the need for service account keys in CI/CD pipelines and external applications. Instead of storing a JSON key file in GitHub Secrets, you configure the GitHub OIDC provider in GCP and grant roles to the GitHub identity. This is more secure because there are no long-lived credentials to leak. IAM deny policies. One of the most significant differences between AWS and GCP IAM is how they handle explicit denies. AWS IAM policies support both allow and deny effects. If any policy denies an action, the action is denied regardless of any allow statements. This is the explicit deny principle in AWS GCP IAM bindings. By contrast, only support allow. You cannot create an IAM binding that denies access. To address this limitation, Google Cloud Platform introduced IAM deny policies as a separate feature. Deny policies work alongside regular IAM allow policies, but are evaluated first. If a deny policy matches, the request is denied before allow policies are even considered. This provides the same explicit deny capability that AWS has in its IAM policies. Deny policies attach to organization, folder, or project resources, and use a different structure from allow policies. They contain deny rules that specify which principals are denied, which permissions are denied, and optionally, which resources the deny applies to. You can also include exception principals who are exempt from the deny. The code example shows a GCP deny policy that prevents anyone except the specified exception group from deleting cloud storage buckets. The denied principals field uses principal set to include all principals in the organization. The denied permissions array lists the permissions being denied. The exception principals field allows the specified group to still perform the action despite the deny rule. This is similar to an AWS SCP, or an explicit deny in an IAM policy. In AWS, you would write a policy with effect deny, the relevant actions, and a condition with string not equals on AWS principal ARN to exclude the exception principals. Deny policies are powerful for creating guardrails that prevent certain actions, regardless of other permissions. Common use cases include preventing deletion of critical resources, restricting access to sensitive data, enforcing compliance requirements, and creating break glass procedures where only specific accounts can perform emergency actions. Organization policies versus SCPs. AWS Service Control Policies and GCP Organization Policies serve similar purposes, but work very differently. Both provide governance controls that restrict what can be done within an organization, but they use completely different mechanisms to achieve this. AWS SCPs are IAM policies that you attach to organization units or accounts. They use the same JSON syntax as regular IAM policies with effect, action, resource, and condition. SCPs do not grant permissions, they only restrict. They define the maximum permissions that identities in the affected accounts can have. Even if an IAM policy grants administrator access, the SCP can prevent specific actions. GCP organization policies work through constraints rather than permissions. Google defines a set of constraints for various services, and you set policies that enforce those constraints. For example, there is a constraint called compute.disable serial port access that prevents enabling serial port access on virtual machines. You can set this constraint to enforced at the organization level, and no one in the organization can enable serial ports regardless of their IAM permissions. The mechanism is fundamentally different. AWS service control policies filter API calls based on actions and resources. GCP organization policies configure Boolean constraints or list constraints that the services themselves enforce. You cannot create arbitrary organization policy constraints. You can only use the ones Google has defined for each service. The code examples show this difference. The AWS SCP explicitly denies specific EC2 actions for instance types not in the allowed list. The GCP organization policy uses a predefined constraint called compute.vm external IP access and specifies a list of allowed projects that can have external IPs. The GCP approach does not reference IAM actions. It configures service behavior directly. Google Cloud Platform organization policies cover areas like restricting resource locations, disabling service account key creation, requiring operating system login for compute engine, restricting which APIs can be enabled, and controlling public access to resources. Each constraint is designed for a specific governance need and is enforced by the relevant Google Cloud Platform service. One advantage of GCP organization policies is they are easier to understand because they are declarative. You say what you want, like resources must be in these regions, rather than writing complex deny policies. The disadvantage is less flexibility since you can only use predefined constraints. Command line interface command comparison. As an AWS power user, you are familiar with the AWS IAM command structure for managing IAM resources. Learning the equivalent G-Cloud commands will help you work efficiently in GCP. This slide provides a comprehensive mapping of common IAM operations between the two platforms. For user and identity management, the concepts differ significantly. In AWS, you use AWS IAM Create User to create an IAM user within your account. GCP does not have an equivalent because Google accounts are managed outside of GCP instead. You manage service accounts with G-Cloud IAM Service Accounts Create. The key parameters are the service account name, display name for a human-readable label, and project to specify which project owns the service account. For role operations, AWS uses AWS IAM Create Role to create an assumable role with a trust policy. In GCP, you either use predefined roles or create custom roles with G-Cloud IAM Roles Create. The create command takes the role ID, project or organization, title, description, and permissions list. To list available roles, use G-Cloud IAM Roles List with the project parameter. Policy attachment is where the biggest syntax differences appear. In AWS, you use AWS IAM attach role policy with the role name and policy ARN parameters to attach a managed policy to a role. In GCP, you use G-Cloud projects add IAM policy binding with the project ID, member specification, and role. The member format includes the type prefix like user : or service account : followed by the identifier. For viewing permissions, AWS uses AWS IAM Get Role Policy and AWS IAM List Attached Role Policies to see what policies are attached to a role. G-Cloud Platform uses G-Cloud Projects Get IAM Policy to retrieve the entire IAM policy for a project, which shows all bindings. You can also use G-Cloud Asset Search All IAM Policies to search for bindings across resources. To simulate or test permissions, AWS has AWS IAM Simulate Principal Policy. GCP offers G-Cloud Policy Intelligence Test IAM Permissions and the IAM Troubleshooter in the console. These tools help you understand why access is granted or denied. The table on the slide provides a quick reference for these command mappings. Keep this handy as you work through GCP IAM configurations, and remember that the underlying concepts differ even when the commands seem similar. Cross-project access patterns. In AWS, cross-account access requires setting up trust relationships between accounts. You create an IAM role in the target account with a trust policy that allows principals from the source account to assume it. The source account identity then calls assume role to get temporary credentials for the target account. This explicit trust relationship is required for any cross-account access. GCP handles cross-project access quite differently because of its unified identity model. Since Google accounts, Google Groups, and service accounts are not scoped to individual projects, you can simply grant them roles in any project where you have IAM admin permissions. There is no need to establish a trust relationship first. If you want a service account from Project A to access resources in Project B, you just add that service account as a member in Project B's IAM policy with the appropriate role. This simplicity has both advantages and risks. It is easier to set up cross-project access because you do not need to configure trust policies. However, it also means you must be careful about who has permission to modify IAM policies, because they can grant access to external principals without any additional approval process. The diagram illustrates both approaches. In AWS, you see the explicit assume role flow where the source account identity assumes a role in the target account. In G-Cloud, the service account from Project A is directly granted a role in Project B's IAM policy. The G-Cloud approach has fewer moving parts but requires careful governance to prevent unauthorized access grants. For organization-wide access patterns in Google Cloud Platform, you can grant roles at the organization or folder level to give principals access to multiple projects at once. This is useful for platform teams that need to manage resources across the organization. In AWS, you would need to set up roles in each account and use tools like AWS Organizations to manage cross-account access at scale. When migrating from AWS, remember that GCP's cross-project access does not require the equivalent of cross-account role assumption. Simply grant the appropriate roles to the identities that need access, being mindful of the inheritance model when granting roles at higher hierarchy levels. Audit logging comparison. Both AWS and GCP provide comprehensive audit logging for IAM activities, but they use different services and log structures. Understanding these differences is essential for security monitoring, compliance, and troubleshooting access issues. AWS uses CloudTrail for audit logging. CloudTrail records API calls made to AWS services, including all IAM operations. Each CloudTrail event includes details like the identity that made the call, the time, the source IP address, the request parameters, and the response. You can send CloudTrail logs to S3 for storage and CloudWatch logs for real-time analysis. Google Cloud Platform uses Cloud Audit Logs, which are automatically enabled for most services. Cloud Audit Logs has three types of logs. Admin activity logs record operations that modify configuration or metadata, such as creating a resource or changing an IAM policy. These are always enabled and free. Data access logs record operations that read configuration or user data, such as listing resources or reading files. These must be explicitly enabled and incur charges. System event logs record Google Cloud Platform system actions like live migration of virtual machines. The code examples show how to query these logs in each platform. In AWS, you use AWS CloudTrail lookup events with the lookup attributes parameter to search by event name. For example, the example searches for create role events to find all role creation activities. In GCP, you use gcloud logging read with a filter expression. The filter proto payload.method name equals google.iam.admin.v1.create role finds all role creation events. You can also filter by resource, principal, time range, and other attributes. GCP's logging query language is quite powerful and supports complex filter expressions. Both platforms support exporting logs to analytics services. AWS can export to Athena for SQL queries on CloudTrail logs. GCP can export to BigQuery for similar analysis capabilities. For real-time alerting, AWS uses CloudWatch alarms on CloudTrail events, while GCP uses cloud monitoring alerting policies on log-based metrics. One important difference is that Google Cloud Platform audit logs include the full IAM policy in set IAM policy events, making it easy to see exactly what changed. AWS CloudTrail includes the policy document for policy-related events, but does not always capture the before and after states in a single event. IAM Recommender and Access Analyzer. Both cloud providers offer tools to help you identify and reduce excessive permissions, but they work differently. These tools are essential for maintaining least privilege access and identifying security risks in your IAM configurations. AWS Identity and Access Management Access Analyzer helps you identify resources that are shared with external entities. It analyzes resource policies on services like S3, identity and access management roles, key management service keys, Lambda functions, and simple queue service queues to find policies that grant access to principals outside your account or organization. It also provides policy validation to check your policies for errors and security warnings, and can generate policies based on access activity. Google Cloud Platform IAM Recommender takes a different approach. It analyzes actual usage patterns over the past 90 days and recommends removing unused permissions or roles. If you granted someone the editor role but they only read permissions, the recommender will suggest replacing editor with viewer. It also recommends replacing basic roles with more specific predefined roles based on the permissions actually used. The diagram shows how these tools work in their respective platforms. AWS Access Analyzer continuously monitors your policies and generates findings when it detects external access. You review these findings and remediate if the access is unintended. GCP IAM Recommender analyzes activity logs, generates recommendations to reduce permissions, and you apply or dismiss these recommendations. In terms of commands, you can list AWS Access Analyzer findings using AWS Access Analyzer list findings with the analyzer ARN parameter. Each finding includes details about the resource, the external principal with access, and the actions they can perform. You review and either archive findings that are intentional, or remediate the policy. For Google Cloud Platform, you can list IAM Recommender insights using gcloud Recommender recommendations list with the recommender parameter set to google.iam.policy.recommender and the location parameter. Each recommendation includes the target binding, the suggested change, and the impact of applying the recommendation. Both tools are valuable for maintaining security posture. Use AWS Access Analyzer to find unintended external access, and GCP IAM Recommender to right-size permissions based on actual usage. In a multi-cloud environment, incorporate both into your regular security review processes. Troubleshooting IAM issues. When access is denied unexpectedly, you need to troubleshoot the IAM configuration to find the cause. Both AWS and GCP provide tools for this, but the troubleshooting approach differs due to the different IAM models. In AWS, troubleshooting involves checking multiple places. You need to examine the identity policies attached to the user or role, any resource policies on the target resource, permission boundaries if configured, service control policies at the organization level, and session policies if using role assumption. The effective permissions are the intersection of all these policy types. AWS provides the IAM Policy Simulator where you can test whether a specific action would be allowed for an identity on a resource. In GCP, troubleshooting is simpler in some ways because there is only one policy model. You check the IAM policy on the resource and all ancestor levels in the hierarchy from resource up through project, folder, and organization. Permissions are additive, so you look for whether the required role is granted anywhere in the hierarchy. However, you also need to check IAM deny policies and organization policies that might be blocking access. GCP provides the Policy Troubleshooter tool, which is extremely useful. You provide a principal, a permission, and a resource, and the troubleshooter shows you whether access is allowed or denied, and why. It shows which bindings grant the permission and which deny policies or organization policies might block it. The code examples demonstrate these tools. In AWS, you use AWS IAM Simulate Principal Policy with the policy source RN to specify the identity, action names for the API action to test, and resource RNS for the target resource. The output tells you whether the action would be allowed or denied. In Google Cloud Platform, you use G-Cloud Policy Troubleshoot IAM with the resource URL, principal email, and permission parameters. The output shows the access state, which bindings were evaluated, and the reason for the result. The Policy Troubleshooter in the console provides even more detail with a visual breakdown of the evaluation. Common issues to check in G-Cloud include whether the role is granted at the wrong hierarchy level and not inheriting to the resource, whether a deny policy is blocking access, whether the principal identifier is correct with the right prefix like user : or service account : and whether the role actually includes the required permission. Best practices for GCP IAM. After understanding the technical differences between AWS and G-Cloud Identity and Access Management, let us discuss best practices that will help you implement secure and manageable access control in G-Cloud. Many of these practices are similar to AWS best practices but have G-Cloud specific implementations. First, use groups for access management. Instead of granting roles directly to individual Google accounts, create Google groups for job functions like developers, data analysts, and security team. Grant roles to these groups, then manage access by adding or removing users from groups. This mirrors the AWS practice of using IAM groups, but remember that Google groups are managed in Cloud Identity or Workspace, not in GCP directly. Second, prefer predefined roles over basic roles. The basic roles of owner, editor, and viewer grant thousands of permissions and violate least privilege. Use predefined roles that match the specific job function. If a developer only needs to deploy cloud functions, grant roles/cloud-functions.developer instead of roles/editor. Review GCP's role documentation to find the most appropriate predefined role. Third, grant roles at the lowest appropriate hierarchy level. Because of permission inheritance, a role granted at the organization level applies everywhere. Grant roles at the project level when access is only needed in one project, at the folder level for multiple related projects, and at the organization level only for true organization-wide functions like billing administrators. Fourth, use service accounts with minimal permissions for applications. Create dedicated service accounts for each application or service, and grant them only the roles they need. Do not use default service accounts, which often have overly broad permissions, like editor. Name service accounts clearly to indicate their purpose. Fifth, avoid service account keys. Use attached service accounts for workloads running on GCP, Workload Identity Federation for external workloads like CI/CD pipelines, and impersonation for development. If you must use keys, Implement rotation and monitor for leaked credentials. 6th, implement regular access reviews. Use IAM Recommender to identify unused permissions and remove them. Review who has access to sensitive resources and whether that access is still needed. Automate access reviews using the G-Cloud APIs to generate reports. Common migration patterns. When migrating workloads from AWS to GCP, you need to translate your IAM configuration. This slide covers common migration patterns that map AWS IAM constructs to their GCP equivalents. For IAM users, migrate to Google accounts managed in Cloud Identity. Set up Cloud Identity. Create accounts for your users or sync from your corporate directory using Google Cloud Directory Sync or Azure AD Sync. Users then sign in with their Google account to access GCP. You do not create users in GCP itself like you would in AWS IAM. For IAM roles used by EC2 instances, create GCP service accounts and attach them to Compute Engine virtual machines. Create a service account with G-Cloud IAM service accounts granted the necessary roles, then specify it when creating the virtual machine using the service account parameter. The virtual machine accesses the metadata server to get tokens just like EC2 accesses the instance metadata service. For cross-account roles, use direct role grants in GCP. If you had an IAM role in account B that account A could assume, in GCP you simply grant a role in project B to the service account or user from project A. No trust relationship setup is needed because GCP identities are not project scoped. For customer-managed policies, create GCP custom roles. Analyze your AWS policy to identify the actions it allows, map those actions to GCP permissions, and create a custom role with those permissions. Remember that GCP permission names differ from AWS action names, so you will need to consult the GCP documentation for the correct permission names. For S3 bucket policies, use IAM bindings on cloud storage buckets. The command G cloud storage buckets add IAM policy binding adds a binding to a bucket. Map the AWS principals to GCP members and the AWS actions to GCP roles. Note that GCP does not support explicit denies in bucket IAM policies. Use IAM deny policies for that functionality. The diagram shows a typical migration path from an AWS architecture with IAM roles and policies to a GCP architecture with service accounts and IAM bindings. The application functionality remains the same, but the identity and access control mechanism changes to fit the GCP model. Multi-cloud IAM strategy. If you are operating in a multi-cloud environment with both AWS and GCP, you need a strategy that provides consistent access control while respecting the differences between platforms. This slide covers key considerations for multi-cloud IAM management. First, centralize identity management. Use a single identity provider like Okta, Azure AD, or Google Workspace as your source of truth for user identities. Configure both AWS and GCP to federate with this identity provider. In AWS, set up SAML federation with IAM Identity Center or direct SAML to IAM roles. In GCP, set up Workforce Identity Federation. Users authenticate once and can access both clouds. Second, establish consistent naming conventions. Use the same names for equivalent roles and groups across both platforms. If you have a group called Platform Admins in your identity provider, map it to similarly named IAM constructs in both clouds. This makes it easier to audit who has access to what. Third, implement unified audit logging. Send CloudTrail logs from AWS and Cloud Audit logs from GCP to a central SIEM or logging platform. This allows you to correlate activities across clouds and detect suspicious patterns that span both environments. Fourth, use infrastructure as a service for IAM. Define your IAM configurations in Terraform or Pulumi, which support both AWS and GCP. This provides version control, change tracking, and consistent deployment processes. You can see the IAM configuration for both clouds in one repository and review changes through your standard pull request process. The diagram illustrates a multi-cloud IAM architecture. The central identity provider authenticates users, who then federate into both AWS and GCP. Each cloud has its own IAM configuration that grants access based on the federated identity. Audit logs flow to a central platform for monitoring. Service-to-service communication between clouds uses Workload Identity Federation so that AWS workloads can access GCP without storing GCP credentials, and vice versa. Fifth, develop cloud-specific expertise on your team. While the concepts are similar, the implementation details differ significantly. Have team members who specialize in each platform's IAM model so they can design appropriate access controls and troubleshoot issues effectively. Security monitoring and alerting. Monitoring your IAM configuration for security issues is critical in any cloud environment. Both AWS and GCP provide tools for detecting risky configurations and suspicious activities, but they work differently. AWS Security Hub aggregates findings from multiple security services including IAM Access Analyzer, GuardDuty, and config rules. It provides a dashboard showing your security posture and compliance status. You can enable security standards like CISA AWS Foundation's benchmark, which includes checks for IAM best practices like MFA on root account and no access keys for root. Google Cloud Platform Security Command Center is the equivalent service. It aggregates findings from security health analytics, event threat detection, and other sources. Security Health Analytics checks for IAM misconfigurations like service accounts with admin privileges, users without MFA, and overly permissive bindings. Event Threat Detection monitors audit logs for suspicious activities. For specific IAM monitoring, you should alert on certain activities. In AWS, create CloudWatch alarms on CloudTrail events for activities like changes to IAM policies, creation of access keys, console logins without MFA, and root account usage. In GCP, create log-based metrics and alerting policies for set IAM policy events, service account key creation, and login events without two-factor authentication. The code examples show how to create these alerts. In AWS, you create a CloudWatch metric filter on the CloudTrail log group that matches IAM policy change events. Then create an alarm on that metric that notifies your security team via SNS. In GCP, you first create a log-based metric using G-Cloud logging metrics create with a filter that matches set IAM policy calls. Then you create an alerting policy using G-Cloud Alpha monitoring policies create that triggers when this metric exceeds a threshold. The alert can notify via email, PagerDuty, Slack, or other channels. Both platforms also support custom security rules. AWS Config has managed and custom rules for evaluating IAM configurations. GCP has custom modules for Security Command Center that you can write to check for organization-specific requirements. Key differences summary. As we near the end of this presentation, let us summarize the key differences between AWS IAM and GCP IAM that you should keep in mind as an AWS power user working in GCP. The fundamental model differs. AWS IAM is policy-centric where you write JSON policies and attach them to identities or resources. GCP IAM is binding-centric where you bind members to roles at hierarchy levels. This affects how you think about and design access control. Resource hierarchy matters in GCP. GCP has organization, folder, project, and resource levels with permission inheritance flowing downward. AWS has a flatter model where service control policies restrict, but do not grant. Always consider hierarchy when granting roles in GCP. Identity management is external in GCP. AWS identity and access management users are created and managed in the AWS account. GCP uses Google accounts managed in Cloud Identity or Workspace. You reference these external identities in Identity and Access Management bindings, rather than creating them in GCP. Roles mean different things. AWS IAM roles are assumable identities with trust policies. GCP roles are permission bundles that you grant to members. GCP service accounts are the equivalent to AWS roles for application identity. There is no explicit deny in standard GCP IAM. AWS policies can have allow and deny effects. GCP IAM bindings only allow. Use GCP IAM deny policies for explicit deny functionality. Cross-project access is simpler in GCP. AWS requires trust relationships for cross-account access. GCP allows direct role grants to principals from other projects without trust setup. Conditions use different syntax. AWS uses JSON condition blocks with operators like string equals. GCP uses CEL expressions that are more readable and powerful. The table on the slide provides a quick reference for these differences. Keep it handy as you work with GCP, IAM, and remember that while the goals are the same, the implementation approach is quite different. Conclusion and next steps. We have covered a lot of ground in this presentation, translating your AWS Identity Access Management knowledge to Google Cloud Platform concepts. Let us recap the key takeaways and discuss your next steps for becoming proficient with Google Cloud Platform Identity Access Management. The most important shift is moving from a policy-centric to a binding-centric mindset. In GCP, you think about which members need which roles at which level of the resource hierarchy. The policy is the set of bindings on a resource, not a document attached to an identity. Service accounts are central to GCP application identity. Create dedicated service accounts with minimal permissions for each application. Attach them to resources and use the metadata server for credential access. Avoid service account keys whenever possible. Leverage the resource hierarchy for efficient access management. Grant roles at the appropriate level to avoid repetition while maintaining least privilege. Use folders to group projects that share access requirements. Use groups from Cloud Identity or Google Workspace for user access management. This allows you to manage access by group membership rather than individual bindings, which scales better and is easier to audit. For your next steps, I recommend setting up a G-Cloud Sandbox project to practice these concepts. Create service accounts, grant roles at different hierarchy levels, and observe how inheritance works. Use the policy troubleshooter to understand how access decisions are made. Set up Workload Identity Federation for your CI/CD pipelines to eliminate service account keys. Review the Google Cloud Platform Identity and Access Management documentation, particularly the sections on understanding roles, best practices, and the permissions reference. Google provides excellent documentation that goes into more detail than we could cover here. Finally, explore the IAM Recommender to see how it analyzes your actual usage patterns and suggests permission reductions. This is a powerful tool for maintaining least privilege over time. Thank you for your attendance. Please consider subscribing to the channel and liking this video.